Hello, and welcome to Burris Agronomy U. We're in our third part of a I guess it's actually going to be a 9-part now series rather than an 8-part series on sulfur, and I'll explain why we're doing that here in a bit. Now, if you've not watched sessions 1 and 2, I would encourage you to do so. That will help clarify some things as we get to talking about this important nutrient, one of the essential nutrients for plant growth. The reason I say this is going to be a 9-part series is because when I looked at this section that we're going to discuss today on plant available sources of sulfur, and I looked at this first section we wanted to discuss, I realized it was just too long, and so I've decided to break it up into a part 3A and a part 3B. Sorry about that, but we're going to go on to a 9-session series, I guess, and with that, we're going to talk about organic sources of sulfur today, and we're going to find out those are fairly important, very important, I should say, in supplying plants with the sulfur that they need each growing season. I'm also going to take a moment here before we ever begin just to remind you where we are in the overall outline of this series. So in session 1, we talked about basic sulfur information, and we talked about the theme that kind of governs this series. In session 2, we talked about plant availability. In session 3, we're building on that last topic by talking about major plant available sources of sulfur. So what things supply most of the plant available sulfur for the plant? And I mentioned again today, we're going to talk about organic material as we move on here in just a second. I'm also going to do one more thing, and that is remind you what the theme for this series is. And that theme is always look to the cycle. Look to the sulfur cycle. Many of the questions we have are answered when we just take some time to understand how the sulfur cycle works. In session 2, we asked, how does the plant primarily take up sulfur? In what form does it take up sulfur? And we answered that by saying it's taken up as sulfate, a negatively charged molecule that's not really held tightly by the soil and tends to float in soil water. We talked before about all the different important things like protein synthesis and all these things that sulfur is involved in, and enzyme activity. We mentioned that plant available sulfur is sulfate, and we're going to mention today that sulfate is derived from many different sources. Not just a couple sources, but many different sources. One quick note here. I should note that grasses tend to be more efficient at using sulfur than do legumes. Now, we just can't begin this session without our perennial pep talk. Our pep talk that circles around this topic right here, this diagram right here. This is the soil sulfur cycle, and we've already admitted it is complicated. It looks complicated, and it is complicated, but we're breaking it into bite-sized pieces. So last time we talked about how sulfur gets into the soil sulfur cycle, and we talked about atmospheric deposition. We mentioned fertilizer as that second source. Today we're moving on to how the plant gets sulfate. Where do those sources of sulfate originate from? Where does sulfate come from? What supplies that plant available sulfur in the soil? And these colored dots represent those original sources for sulfate. So we do have atmospheric deposition here, we do have fertilizer here, but we also have some other important and maybe less important sources of sulfate for the plant. Now, I would say that there are really 3 major sources and 2 minor sources for sulfur as you look at that diagram. And today we're going to venture into the first part of the major sources. I do want to at least get you accustomed to these major sources of sulfur for the plant. Organic material, atmospheric deposition, a topic that we mentioned in passing last time, and fertilizer, a topic that we also mentioned last time, I should say in session 1. I've kind of mapped out here my view of what really becomes most important for supplying sulfur to the plant. And I want you to notice that one of the most important sources of sulfur for the plant is actually not fertilizer. It's not atmospheric deposition. One of the most important sources of sulfur for the plant is organic material, dead plant and animal material in various states of decay in the soil. That actually supplies most of the sulfur that we need for that plant. Then we have atmospheric deposition as a big second source of sulfur, and then we have our fertilizer amendment that we put into the soil to kind of augment the sulfur situation for us. I just don't think it's much fun if we have these discussions without talking about things that are practical, real world experience. And I want to use one of those real world experiences as the background for our discussion today. So let me ask this question based on real world experience. Why do we get a little sulfur-related chlorosis, that's a fancy word for yellowing, each spring? Why does it eventually pass? Why do we get it? Why does it eventually move on? Now, you already know my answer to that question, and my answer is look to the soil sulfur cycle. And in particular today, we're going to look at organic sulfur. Remember, I said that's a big source of sulfur for that plant. Now, in order for organic sulfur to be made available to the plant, remember, I said this is dead plant and animal material in various states of decay. We actually have to get decomposition kicking into gear pretty good. We call that mineralization. We basically have to break apart that material and release the sulfur that's tied up within. We have to go through that step first before the plant can latch on to that stuff. And so we go through a process called mineralization, and a big part of mineralization is what we call bacterial oxidation. So organic sulfur sits there, it starts to get chewed up by this bacterial oxidation, and then eventually we get sulfate available to the plant, it's able to take it up, and we get to the point we want to get to. We could just leave it there if we wanted to, but we're not going to do that. I want to go a little bit deeper into this topic of bacterial oxidation of sulfur. So as we mineralize, as we release sulfur, and bacterial oxidation occurs to make that sulfur transform into a plant available form, into this form we call sulfate, I want to talk about that just a little bit. You can see the chemical formula for that process right here, and I don't want you to get wrapped up in the chemical formula. What I want you to notice is for us to get sulfate, for these bacteria, these thiobacillus bacteria to be active, we're going to need a little bit of oxygen, and that means we can't have wet conditions. If we have super wet conditions, that's just not the right environment for these bacteria, and they will not do a good job at converting sulfur over to sulfate. They won't do a good job converting sulfur over into the plant available form. Now, we've mentioned this before, and I want to mention this again. This really does have a lot of similarities to the nitrogen cycle. For nitrogen to be converted into nitrate, we have to have oxygen. We talk about denitrification, requiring waterlogged soils, requiring the absence of oxygen. But for us to get nitrate, we have to have some oxygen. And so here again, we have a real similarity between the sulfur cycle and the nitrogen cycle. The point I want to make here, though, is when we're talking about saturated conditions, kind of tying up sulfur, not getting it into that plant available form, we start to have part of the explanation for why we see that spring yellowing. This is another important piece to the puzzle, though. Bacteria are driving this process. For us to get sulfate, that plant available form of sulfur, we have to have bacteria driving that process, or it just doesn't happen. The bacteria are the ones that are active in this thing. And so because of that, this is inherently a biologically driven process. And as soil temperatures go up, the bacteria have a great time and are able to do that conversion over to sulfate very efficiently. As the temperatures cool down, those bacteria really don't like those cold conditions. We don't like cold, they don't like cold. And so because of that, they slow down and they really don't convert things over to sulfate very well. You can begin to see the reason for the yellowing and then the passing of the yellowing that we see annually. In the spring, we have more moisture and cooler temperatures. The bacteria are less active. There's less sulfate available at that point. And then we have the summer move in. Temperatures kind of go up, soils dry out a little bit, and those bacteria kick into gear, supply plenty of sulfate, and that plant greens up after that brief yellowing spell. We want to get this thing right, and so we probably should add a couple more layers to this discussion of why we see the springtime yellowing and then this greening up. There's also a biological component associated with the plant. If you look at a corn plant, for instance, the seminal root system is fairly shallow, that root system that sprouts from the seed. Later on, we have the nodal roots, which start to drive down into the subsoil, which tends to be higher in sulfate, and so it's also partly explained by this root growth that kicks into gear. We start seeing that nodal primary root system kick into gear, get down to sulfate, and helps green up the plant as well. I don't want to go too deep into soil science here, but I do want you to notice, if you're familiar with chemistry at all, you see that hydrogen cations, 4 of them actually in that formula, are created by the activity of thiobacillus. And the point is that this conversion of elemental sulfur into sulfate, of sulfur into sulfate, actually causes some acidification. And these thiobacillus bacteria have actually evolved so that they can withstand those low pH environments. I cannot overstate how important the activity of thiobacillus is. These bacteria are critically important to mineralization, the tearing apart, the breaking apart of organic material so that it releases the sulfur within, making it available to the plant. This supplies a lot of the plant's needs, maybe 5 to 12 pounds of sulfur, plant available sulfur per acre per year. A good rule of thumb, each percent organic matter equals 3 to 5 pounds of plant available sulfur per season. Bacteria really are that important, and I cannot overemphasize how important the activity of thiobacillus is. I keep mentioning that. But they're not the only players. Other things also work on organic sources of sulfur and transform it into sulfate. And one of those other sources, one of those other players, I should say, are soil enzymes, materials that allow us to have a chemical reaction at a low temperature called sulfatases. Now, these soil enzymes are created by other living organisms in the soil and released into the soil. They're fairly stable, last for a while, but they do act on these organic sources and help release sulfate. Now, this is somewhat similar again to urease, actually converting over urea into ammonia in the nitrogen cycle. So again, we see another parallel to the nitrogen cycle here. But there are these enzymes that are active in the soil. Bacteria are the big players in this conversion, but these enzymes play a role as well. As we close things here, we'll just emphasize one more time that most of the plant's sulfur needs come from organic material in the soil and the breakdown of that organic material in a process that we call mineralization. And that's primarily driven by bacteria, these thiobacillus bacteria. And so because it's a biological process, temperature and moisture influence how easily we have that conversion over to sulfate, that breakdown of organic material and release of that sulfur within in the form of sulfate. We should mention here as well that sulfur mineralization occurs more rapidly in non-fallow ground than in fallow ground. Now that's the close of Part 3A. Again, apologies for making this a 9-part series. We're going to move into Part 3B next time, where we're going to talk about fertilizer sources of sulfur as another major source, and before that, the big second player in plant available sulfur sources, atmospheric deposition. We'll cover those 2 points next time. Until then, thanks for watching, and we look forward to visiting with you again on Burris Agronomy U.